Hi everyone. We're going to take a look at the review sheet that you have for the Thermochemistry and Kinetics test that we're going to take on Thursday the 30th. I'll probably break this up into at least 2 different videos so that each will be short enough to post really quickly on eClass. So let's take a look at what we've got. Now, you got this early in the week or perhaps last week at the end of the week. So let's just kind of run through a couple of the definitions here really quickly. What is heat? We've talked about several times that heat is a form of energy. Heat is a form of energy. Okay, heat is a form of energy that can be used to cause chemical reactions. Heat might be given off by chemical reactions, which leads us to the next one. How is heat calculated? Well, heat ultimately for whatever chemical reaction we have is going to be a change in Q, the change in our heat, the change in our energy that's given off, and we would calculate that by taking a look at whatever the energy of our product is and subtracting the energy of our reactants. And that's going to either give us a positive or negative energy change, which will tell us whether or not that reaction was endothermic or exothermic. So what about specific heat? Specific heat is the heat that is necessary to raise 1 gram of a substance 1 degree Celsius. So specific heat of a substance, and the specific heat of a substance is a characteristic of that substance. Each substance has its very own specific heat. Okay, each substance has its own specific heat, so that it is an identifying characteristic. And it's the amount of heat that's necessary to raise 1 gram of that substance 1 degree Celsius. What are the units for specific heat? Well, we've talked about 2 different units for specific heat. This could be calories, as in lowercase calories per gram degree Celsius, or more often, all of our calculations are going to be in joules per gram degree Celsius. Well, what's the relationship between calories and joules? 1 calorie equals 4.184 joules. What is temperature? Temperature is a measure, it's not the same thing as heat. Temperature is the measure of the average kinetic energy of the particles in a substance. A measure of the average kinetic energy of the particles in a substance. If the particles are moving more quickly, that's more energy, which means that the temperature is higher, which means you experience that as more heat. You have a higher amount of energy that's in that substance if it has a higher average kinetic energy. Are heat and temperature the same thing? No, we just said that. Explain. All right. Heat is a form of energy. Heat is a form of energy. It's not the only form of energy, but heat is a form of energy, whereas temperature, as we just defined, is a measure of the average kinetic energy. So heat is energy, temperature is a measure of that energy. All right, so let's look at the state changes of state. Okay, this would be going from solid to liquid to gas, and if you remember, we had a little triangular diagram, okay, and you could put gas, liquid, solid, okay, and think about what's going on in each of these situations, because you can go in either direction, right? A solid can become a liquid if it loses kinetic energy. If it loses energy, it can become a liquid. Okay, I'm sorry, if the solid gains energy, it's going to become a liquid. If it gains energy more, it's going to become a gas. A gas can become a solid, and that is called that's a special case right there, but a gas can become a solid or a gas can become a liquid. If a gas becomes a liquid or a solid, it's going to be losing energy. If a solid becomes a gas, it's going to be gaining energy. If a solid becomes a liquid, it's going to be gaining energy. So let's think about the names of these things. Well, going from a solid to a liquid, you often would call that melting, but we call that fusion. Solid to liquid, fusion, requires an energy input. Liquid to gas, evaporation, also requires an energy input. So that's endothermic, is moving in this direction. So from solid to liquid to gas, that is endothermic. All right, we could go from gas to liquid by losing energy, so that's exothermic. Gas to liquid, liquid to solid also losing energy. So what about the names of those? Solid to liquid, we already said, was fusion. Liquid to gas is evaporation. Gas to liquid, condensation. Liquid to solid, solidification. Probably call that freezing. Now, what about these two directions over here? Obviously, if a gas is going to a solid, it's got to lose a lot of energy, so that's exothermic. Okay, and that would be called deposition. From a solid to a gas, that's got to gain energy, and that would be called sublimation. So let's come over here to our chart. Ice cream on a hot summer day melting. Well, if it's melting, if it's melting, we refer to that as fusion. If something is going through fusion, it is going from a solid to a liquid, and in order to do that, it must absorb energy. So that is an endothermic reaction. Boiling water. When water boils, that is evaporation. That is going from a liquid to a gas, and you're still putting energy into it, so that is an endothermic reaction. Steam in a shower hits the mirror or hits anything else and turns into a liquid. Okay, so that's going from a gas to a liquid. It's going from a gas to a liquid. It's got to give off energy, so that is an exothermic reaction, because a gas has more energy than a liquid does, and that is called condensation. Formation of sleet from rain. Well, sleet is ice, rain is liquid, so this is going from a liquid to a solid. Liquid has more energy than a solid, so it has to lose energy, so that is an exothermic reaction. This is freezing, so we call this solidification. So there are your state changes. All right, so let's take a look at number 5 and number 6, which have to do with calculating various things having to do with that equation, Q is equal to MC delta T. So what does this equation ask? What is this question asking? An unknown solid with a mass of 248 grams is heated from 22 degrees to 68.5 degrees, and it absorbs 2,730 joules of heat during this process. What is the specific heat? Well, obviously in this equation, we're not solving for Q, we're solving for the specific heat, which is C, because this is heat is equal to mass times the specific heat times the change in temperature. So we're given a heat, so we've got to put this over here where the Q is. So 2730 joules is equal to M, 248 grams. We want to know specific heat because we don't have that. And then our change in temperature is equal to temperature final minus temperature initial. So our 68.5 degrees minus 22 degrees gives me a change in heat of positive 46.5 degrees Celsius. So now, did we go up or down? Well, an unknown solid with a mass of 248 grams is heated from that temperature to that temperature. So it's getting hotter. We're putting energy into this, so it's going to be an endothermic reaction, which means that that temperature change is positive, which makes this positive over here. Well, that's good because we already said that this is absorbing that. Since it's absorbing that, we know that it's endothermic anyway, and so it should be positive. Like I showed you on the video where we were simply solving these equations right here, I would simplify this as much as possible on this side before trying to solve for the variable, which is C here. So 248 times 46.5 is going to give me 11,532 times C is equal to 2730. Now notice I've taken the units out really quickly so that we can just see the equation so that we are clear with the math and what's going on. From this point, you know, to simply solve this equation, we have to divide both sides by 11,532. So that's going to give me a C is equal to 0.237. So put this back into context, and we have 0.237 joules per gram degree Celsius, because what was this asking for? This was asking for the specific heat. What is the specific heat of this unknown substance? Well, that's what we calculated to be our specific heat. So let's look at this chart. Which one of these is the closest to that? Well, that's going to be the closest, which is silver. So our unknown substance here is most likely silver, because that's the closest that we could come to that. Continuing along, let's continue this type of problem. And we're still using our formula Q is equal to MC delta T. So let's take a look at, we're given 785.2 joules of heat are released. Now, how is that different from the problem that we just saw? The problem that you just worked, the temperature, you were not releasing that, but you were absorbing that much heat. Well, if we're releasing it, this means our heat is going to be negative. So in this case, our temperature, or our the Q is going to be negative. So minus 785.2 joules. Now, it's going to be negative because it's releasing this heat. It's releasing it. It's being taken away from it. That's why it's a negative is equal to, is released by 98.5 grams. So there's my mass, 98.5 grams of liquid ethanol with a specific heat of 2.44 joules per gram degree Celsius. So there's my specific heat, 2.44 joules per gram degree Celsius. And I want to know what the change in temperature is. Calculate the change in temperature, yes. So ultimately I'm going to calculate my change in temperature. Is this process endothermic or exothermic? Well, we have released heat, so it is an exothermic reaction. Well, this makes sense because my heat over here is negative. If this heat energy is negative, that means that it's released it, which means it's exothermic. Now, going on to B, calculate the change in heat. So our we have Q is equal to MC delta T. We've plugged in everything here. What we have then is going to be, let's see, negative 785.2 is equal to 240.34, and I got that simply by multiplying this 98.5 times 2.44 to give me this, and of course times delta T, because this is what I'm trying to solve for. Divide both sides of this equation by 240.34, and I come up with a change in temperature of minus 3.27 degrees Celsius. So that would be my, so in other words, this substance lost 3.27 degrees. So it cooled down by 3.27 degrees Celsius in order to lose that amount of energy. Determine the amount of heat required to raise the temperature of 35.1 grams of gaseous ammonia from 28 degrees to 28.32 degrees to 36.98 degrees. All right, so determine the amount of heat. Well, this time then I'm actually looking for my Q. So Q is equal to MC delta T. So I don't know Q, but I know my mass, 35.1 grams. I know the specific heat, it's right here in the problem, 2.09 joules per gram degree Celsius. And I know my change in temperature. Change in temperature is equal to temperature final minus temperature initial. My final temperature is 36.98. My initial temperature was 28.32. So my change in temperature is 8.66 degrees Celsius, and that is positive because 36.98 minus 28.32 is positive 8.66. So when I multiply all three of these together, what I end up with is Q is equal to 635.29 joules. So that's how much energy would have to be absorbed in order to get this amount of liquid gaseous ammonia from 28.32 degrees Celsius to 36.98 degrees Celsius. Then finally, our last Q is equal to MC delta T problem. What mass of liquid mercury? So this time we're going to be solving for M, which has a specific heat of 0.140 joules per gram degree Celsius, would release, all right, so I'm just going to go ahead and start writing here, release 1,895 joules. All right, so I've already got my mass. Let's see what mass, that's what I'm looking for. My specific heat is 0.140 joules per gram degree Celsius. And my change in temperature, temperature changes from 65.12 to 43.09. Well, take a look. It's going from 65.12 to 43.09, so that means my final temperature is less than this. It's cooling down, so my change in temperature is going to be negative. And when I take 43.09 and subtract 65.12, I get my change in temperature of negative 22.03 degrees Celsius. So when I multiply these two together, and then subtract, and then divide what I get from this product, I divide both sides so that I can get this, get everything on here and the M by itself, and I get a mass of 86.02 grams. So it would take 86.02 grams of liquid mercury to release 1,895 joules of heat energy as it drops 22 degrees Celsius. All right. Now that brings us to, now, if you had problems working any of these questions, please go back to the video from my video from last week, Tuesday or Wednesday, I believe, where I worked problems solving for Q, solving for M, solving for C, and solving for delta T. So go back and take a look at that video, and you can see solving for each one of those variables. Okay, I worked several problems where you had to, you might have been solving for the Q or the M or the C or the delta T. You could have been solving for any one of those. Okay, so now let's take a look at this heating curve. Well, before we even start answering any questions about the heating curve, let's walk through this heating curve and just kind of point out some of the things that we see. Okay, to start with, here's our time in seconds down here and temperature. So if we look here at L, the temperature is increasing as time increases, and then we've got, which means that whatever the substance is that's here, the temperature is rising, and the temperature rises until we get to this point right here. Well, the temperature plateaus right here. So the temperature of the substance isn't rising at all, which means at this point we're adding potential energy to this substance. Well, then once we reach a certain point of energy, potential energy right here, we start to increase the temperature again. Well, what was it that we said temperature was? The average kinetic energy. So whenever the line is sloped, we're increasing kinetic energy, or decreasing, depending on what direction we're moving here. If we continue to go to the right, here we're at potential energy again, and here we're at kinetic energy again. All right. So what's going on at these places where we're increasing our potential energy? This is where we're having a phase change. In other words, it could be going from a solid to a liquid. It could be going from a liquid to a gas when we have these plateaus. So, assuming that we have something here that is on Earth and it's simply going to go from a solid to a liquid to a gas, we can label the parts of this heating curve appropriately. All right? Well, here the temperature is rising, so our kinetic energy is going up, and it's at the lowest temperatures. So we're going to say that down here we have a solid. And that solid is increasing in temperature as we go to the right. Well, what's going on then here at M? Well, it's not, the temperature is not going up anymore. So what's that energy doing if we continue to put energy into it? Well, it's making this solid into a liquid. So here at M, solid is going into a liquid. So at M, we have both a solid and a liquid, and we're increasing potential energy. Remember, L here was kinetic energy. Well, once we get to a certain point here, we start to increase our kinetic energy again. In other words, the temperature is going up again, because the temperature is a temperature, it's going up. You can see it's increasing, going up a slope. So here, we've gone from a solid to a liquid. So at N, everything's a liquid. Well, what happens when we get here? Well, what happens to a liquid when you continue to add energy to it? It starts to evaporate, which means that here we have another plateau. So that means that this liquid, whatever it is, it's evaporating. So now I've got both a liquid and it's changing into a gas. So I have a liquid and a gas, and we're getting this potential energy increase again. And then once everything has turned into a gas, we're back to a sloped line. So now my temperature is increasing again. So I'm increasing my kinetic energy again. And everything here up at this top, where the line is increasing, everything here is a gas. So we have gas, we have liquid to gas, we have liquid, we have solid to liquid, and then down here we have solid. So now that we've identified all of those spots, let's go back. Now let's answer our questions, and chances are we've probably just answered all of our questions. All we have to do is write it down. On this heating curve for benzene, what do the plateaus represent? Well, plateaus are the flat areas. Well, here's a plateau, we're going from solid to liquid. Here's a plateau, we're going from liquid to gas. So what do the plateaus mean? That means that you have a phase change. You're going from one phase of matter to another. We're also increasing kinetic energy. Potential energy. We're increasing our potential energy in those plateaus. So, what state of matter is represented by L? L is down here, so that's a solid. We've already said that. What state of matter is N? N is here. Got a sloped line, so my kinetic energy is increasing, so that represents a liquid. What about for P? P is up here. We've got a sloped line again, and the temperature is increasing. That represents a gas. What letter represents fusion? Wow, well, fusion is probably one of those words that you're not used to using, but remember what fusion is. Fusion is what we would use for melting. So melting is when we go from a solid to a liquid. Well, we're up here on the chart that we have things going from a solid to a liquid. Well, look right here. It's a solid here where the temperature is increasing. Once it reaches this point that is the common, melting freezing point, we have a solid and a liquid. So fusion, which is solid and liquid, solid going to liquid, that's going to be at letter M. Well, what about solidification? Well, solidification is freezing. Well, what would happen if you were going in that direction on this graph? Solidification is the same thing as fusion, only going in the opposite direction. So solidification also will be M. Condensation. What's solidification? I'm going to go ahead and put that down here. That's liquid to solid. Condensation. Condensation is gas to liquid. Well, where up here do we see a gas going to a liquid? Well, I see liquid going to a gas if we're going in that direction, but if we're going this way, gas going to a liquid, so we have this O. What letters represent kinetic energy? Well, if we're increasing kinetic energy, that means that the temperature is increasing. Well, if we're decreasing kinetic energy, that means the temperature is decreasing. Well, at the plateau, the temperatures aren't changing. Where is the temperature changing? Anywhere you have a slanted line. So L, N, and P would be your increases or decreases in kinetic energy. Well, what about potential energy? Well, potential energy is when we have all of the energy going into it to change its phase. We're not increasing the kinetic energy because you can see there's no change in temperature. So it's M and O. All right, look at the last question on this page. Why is it that when you bite into a cherry pie, the crust doesn't burn your tongue, but the pie filling burns your tongue? I'll tell you what, we're going to stop this video and you're going to have to take a look at part 2 in order to learn that.